Welcome back to our series on field axioms. This is part 2. In this segment, we'll be zeroing in on the identity, inverse, and distributive laws. Let's dive in. Let's start off with the identity laws: additive identity and multiplicative identity. The identity laws state that there exists a number that doesn't change a value for that operation. That is, the number is identical to how it started. 0 is the additive identity. When you add 0, the value does not change. For example, 12 plus 0 is 12, x plus 0 is x, and 6x plus 0 is 6x. One is the multiplicative identity, as when you multiply by 1, the value does not change. For example, 12 multiplied by 1 is 12, x multiplied by 1 is x, and 6x multiplied by 1 is 6x. Let's continue on with the inverse laws. We have the additive inverse and the multiplicative inverse. The inverse laws state that for a given number, there exists another that we can use the operation to get the identity. That is, the opposite of the number. Let's start with the additive inverse. The additive inverse of a number is the number with the same magnitude or size, but is in the opposite direction on the number line. The additive inverse of a positive number is the negative number with the same magnitude. The additive inverse of a negative number is the positive number with the same magnitude. For example, for positive 4, the additive inverse would be negative 4, as positive 4 plus negative 4 is equal to 0. A number and its additive inverse are sometimes together called a zero pair, since they add to 0. We can simplify calculations involving addition and subtraction of positive and negative numbers by using zero pairs. This involves breaking the number with the larger magnitude into a smaller part, which is the additive inverse of the smaller number, and the remaining amount. This technique helps streamline the arithmetic process and makes it easier to work with positive and negative values. For example, positive 7 plus negative 12 is equal to positive 7 plus negative 7 plus negative 5. We make a zero pair from the 7s, and we add the additive identity 0 to negative 5. The additive inverse also allows us to write any subtraction as an addition, to then be able to take advantage of the commutative and associative laws for addition. The difference of two numbers is not changed when the same number is added to both numbers. So, by strategically adding the additive inverse of the subtrahend, the number we are subtracting, we can make it equal to 0, leaving an addition. Moving on to multiplicative inverse. This tells us that when we multiply by the inverse, we get 1. The multiplicative inverse of a number is also known as the reciprocal. For example, the multiplicative inverse of 2 would be 1/2, as 2 multiplied by 1/2 is equal to 1. Similarly, the multiplicative inverse of 3/4 is 4/3, as they multiply to 1. The multiplicative inverse allows us to write any division as a multiplication, to then be able to take advantage of the commutative and associative laws for multiplication. The quotient of two numbers is not changed when the same value is multiplied to both numbers. This is more obvious when the division is written as a fraction. So, by strategically multiplying the multiplicative inverse of the divisor, the number we are dividing by, we can make it equal to 1, leaving a multiplication. The identity and inverse laws are useful concepts when students come to solving equations, as they will need to balance equations to solve for an unknown, using inverse operations that result in identities. Finally, let's talk about the distributive law. The distributive law connects addition and multiplication, and through the identity and inverse laws, subtraction and division, and gives our convention of how to order calculations involving both addition and multiplication. Specifically, we say that multiplication distributes across addition, so that we can either multiply by the sum or multiply by each term. In the arithmetic, students show the link with order of operations by adding what is in the brackets first and then multiplying by 3. Arrays are a useful way of representing this. 3 lots of 2 plus 4 is the same as 3 lots of 2 plus 3 lots of 4. This shows how the 3 can be distributed and multiplied by each term in the brackets. This is the same process we use to multiply with multi-digit numerals. The array used before to demonstrate the distributive law can be extracted to the area model, shown here, where we no longer see the individual parts, but write the values instead. For example, when multiplying 34 by 6, 34 can be separated into 30 plus 4, creating the equation 6 times 30 plus 4. These can be multiplied separately as 30 times 6, 4 times 6, and then added together to get 204, rather than directly evaluating 34 multiplied by 6 using repeated addition, for instance. The distributive law also works in the other direction to group several products that have a common factor. For example, instead of multiplying both of 7 and 13 by 8 and then adding them together, we can first add the 7 and the 13, then multiply the sum by 8. You may have known many of these axioms individually, either explicitly or implicitly, as properties of numbers. The benefit of grouping them together under the banner of field axioms allows us to refer to them more briefly as a collective, and let's be honest, it's easier to write. Throughout these videos, you have seen that the field axioms can be applied in a range of ways with arithmetic, percentages, and algebra to allow students to develop a deeper understanding of the rules that underpin arithmetic.